Well, welcome everyone. If you don't know who I am Ann Wright. I am the Education Director here at Artisan's Asylum. I want to welcome everyone here today on this Zoom session. So this is the first in what hopes to be a promising series of virtual sessions, hearing from members, artists, creative folks who have something to say. I approached Bob and Jacob, maybe 2 months ago, about potentially speaking about this. I had happened across them working on some of their experiments here in our social area, close to where Bob is right now, and got to see a little bit of behind the scenes, but didn't really fully grasp what had actually happened until Mark Roper's video came out. And then I got to watch it and I was like, oh, I got to see some of this. And I also got to hear about the times that they did some experiments in our loading dock. And we, as staff, found out a little bit later. So the intent of this is, as we're all sort of, in our homes and not able to connect and find inspiration and creative inspiration, being able to provide a little bit of that. On top of that, because I'm always thinking about education, this is a bit of an opportunity here where we don't often think about sort of informal learning in the ways that social media can invite curiosity, can invite sort of a sense of whimsy and fun about, these topics like science and mathematics and engineering. And we're very, very fortunate to have Bob and Jacob as part of our membership. So they were supposed to send me their bios before this and I didn't get them. So I'm not going to be able to do
I missed that.
introduction. So what I am going to do is I'm going to ask them to give us a 30-second bio about themselves. And then just logistically, what's going to happen is our agenda is they're going to be able to share a little bit more about the behind the scenes of the Mark Roper video. Hopefully I sent that out. I included that in the description. So people have hopefully gotten a chance to see that. And also on our internal list, Jacob included or sent over to me another video. So we can always drop that in the chat for people to watch after this session, or pull it up on a tab and you can go ahead and watch it afterwards. So they're going to talk till about 7:10, sharing their experiences. I have a few questions for them after that. It's no secret, I sent them the questions ahead of time so that they can prepare a little bit. And then about 7:20, the last 10 minutes of our session here, we'll open up the questions to you guys. What I hope you'll do, well, it's kind of an informal group, so we can probably just have you guys shout out questions here, and I'm sure they'd be happy to answer. If it was a larger group, I'd say we'd throw it in the chat box, but we're a small family bunch right now. So I'm going to turn it over to Science Bob and Jacob. 30-second bios for each of you, and then go ahead and kind of start in with your presentation. Bob, I know you said you wanted to give a little bit of context and background, correct?
Yeah, after intros, I can kind of give you the origin story of this crazy video. My name is Bob Pflugfelder, and the day job is an elementary school science teacher, and then the nighttime Batman job is to find ridiculous ways to demonstrate science, which apparently caught the eye of TV producers over the years and YouTubers. And so I am at my space in the Artisan's Asylum. Well, in my space, at least 12 feet, I see no humans around me. I'll put on a mask if anyone gets close. And so, yeah, we build stuff. There's lots of clips on YouTube from various shows. And this is kind of where it all comes together.
I'm Jacob. I am an electromechanical engineer during the day. Right now I'm working in the space industry doing satellites and things like that. I after my day job, like to build props and models and basically just fabricate things. I've been working on a bunch of pretty cool projects recently in the last 2 years or so. I don't know if any of you have seen the Marble Machine X. It's a super complicated, basically completely kinetic musical instrument that a guy in Sweden is building with about 70 engineers all over the world. I work on a bunch of different props and models and costumes and things like that. I dabble in a little bit of everything, and I like to think of myself as sort of not necessarily a materials expert, but I have a very large knowledge of different types of materials and what we can use them for.
Yes, he does.
So take it away, Bob.
Oh yeah, so here I'm going to show you why we're all here, at least part of it. If you haven't seen it, here's sort of a highlight of what we're checking out.
Down to this moment. Here we go. 3, 2, 1.
So through many edits, you kind of get the idea there. So what I thought, this basically came about because hold on.
Run from the bottom.
So this came about from I had done this experiment. It was my very first time on Jimmy Kimmel, and this was an experiment I did. And apparently no one had done it in this flask before. And so people started doing it. I met Mark at a convention for YouTubers, and we talked a little bit about this experiment. He's like, someday I want to just blow this thing up and just like make it crazy. Never thought another thing about it. And then last summer, 2 summers ago, he said, hey, I want to do it, but I want to do it in a swimming pool. And so we did that. And then he said, oh, I want to do this in a gigantic flask. And again, I never thought it would. And sure enough, towards the end of the summer, he called me up and said, let's start doing this.
So what is the experiment, Bob?
So the experiment is known as elephant's toothpaste. It is a chemical reaction that uses hydrogen peroxide and a catalyst, and it creates massive amounts of foam in this chemical reaction. And we wanted to see what it would look like. Could we scale it up? And just to give you, I can give you a little bit of, hold on a second here. I'll show you what the, I'm pretty sure I have it. What the actual, I do have it somewhere. I'll bring up the small scale version.
So
but, go ahead.
One of the first experiments I helped Science Bob with after I met him was doing this at, I think, some convention, a small version of this in a flask that's usually what I think we said it's 14 inches tall, 18 inches tall.
About that.
Yeah, so there are various different, while you find that, I'll just talk a little, Bob. There are various different like concentrations and intensities of catalysts that you can use that will cause different reactions. Bob has a version where you can do it at home with some dish soap and some yeast, and that is a very mild, sort of slow foam creation. And when you change your catalysts, depending on what you use, it increases the speed of the reaction. So let's see if he can find that there.
Okay, we'll bring it up here. This is the small scale version. And this was discovered completely by accident. Hold on a second, sorry. This was discovered completely by accident. Mostly, it used to be done in a flask, in a graduated cylinder. But I did it in a flask, and the effect was just like amazing. Shot up in the air. It was like the perfect television experiment. Give me one more second here. It's gonna go black for a second.
When it goes in a cylinder, it basically just goes straight up in the air. And I had seen that experiment before, and when Bob showed me the flask version of it, made a lot of sense from like the physics and engineering side. So a flask is shaped like a cone, and as it goes up, it decreases in diameter. So the pressure or velocity of the foam has to increase to get out. So if you can see his video, it's slow-mo there.
Check a little video of it, and it might be a little bit long here. So this is what we kind of referred to as the ideal. This is what we are kind of trying to replicate. Get to here, maybe. The one slide I forgot to actually put into this presentation. All right, keep going. Turns out it's not the right one.
Isn't it just super slow?
It is, but I don't think I'm not seeing the actual reaction here as I scrub through it. But it does anyway. So the big question was, can we actually? Is there a way to scale this up? And can it scale? Can we just like scale it up? And I knew at that point that there's no way I was going to be able to do this alone. I didn't have experience fabricating at a scale where we really need to keep track of the science and keep track of the build and do stuff in CAD. And that's when I came to Jacob and I said, I think I got a fun little project. I would say from build to experiment, from, hey, let's do this to experiment was 3 months, 3.5 months, maybe.
I think it was, yeah, about that. Hold on, I found the Jimmy Kimmel version.
We got lucky because, oh, look, there I am. We got lucky because because he got COVID. Mark Rober got COVID, and that bought us about an extra week and a half.
Right.
There it is. So there's the classic.
So it goes pretty, it got on the ceiling of the studio in that one, right?
It did. It literally went higher than we expected it to.
Yeah, so I'd helped Bob with a number of other projects for Jimmy Kimmel's show and just in general. And one of them in particular was a world record. And, you know, when you help out with a world record, it's kind of not fun if you don't get to actually be on the world record. So I said, Bob, if there's ever another time when you get a chance to make a world record, I am helping you with it. So that was one reason why he asked me, but also because I like working with him and we work well together. So Bob came to me and was like, so I finally got that call, because he'd mentioned to me a long time ago when we actually both met Mark at the same convention, that he was considering scaling it up. And like I had done some sketches at the time, just like kind of off the cuff, trying to figure out how I would do it. And so when he's like, okay, this is definitely going to be a thing, I was like, so who's paying for it? That was the first question, because when you scale something up, it gets more expensive. But so yeah, that's where this all started. So my first question was, how big are we talking? And Mark says, I don't know, something like 20 feet. And so my first reaction was, okay, that's quite a lot bigger than I expected him to say. And I don't know if you thought it was going to be that big either, Bob, but so I started to do, I'll share some more images, and this is actually going to sort of answer one of the questions that you were going to have, which is our process. We can kind of go through that a little bit. So let me share my screen again real quick. So the first thing I did was I went into Fusion 360 and just kind of took a screenshot of the flask, the tabletop size flask, which we knew for volume, and then I mocked it up and scaled it up. So this one's about 4 feet tall. And this is actually like probably the 6th or 7th version of this to the geometry that we finally decided on. But we kind of iterated through sketches of like what shapes the sides were going to be, what size each side was going to be, how we're going to connect the sides. And all of that was really the core of this project. The problem solving of how to make this thing hold pressure was something that we kind of discovered along the way. So without going too far into detail, we made one version, we ordered all the parts, and it worked like pretty well, right, Bob? I can pull up a clip of that if you don't have it up.
I've got that here too. And by the way, if you've got a specific question about something that we're talking about, by all means,
yeah, you can chime in.
throw it in the chat. Throw it in the chat.
Down.
So here is
So with the
hold on.
largest.
Here's our 5-foot version. That I
Wait,
can
why are
show
you using
you.
Mark's video, Bob? I did a whole video on all of ours.
That's true. Here is our 5-foot version.
That wasn't the first one, though, Bob. We got to show the first one.
Yeah, that's true. This is the second 5-foot version.
Is it? I don't think it
should
is, Bob.
What's that?
I don't think that's the second one either.
What is that one?
I think that's the third, because the second was blue. Okay, I've got it in order, Bob, so I'll pull it up.
Jacob has it in order. Do you have it in front of you in order?
Yes, I do. So the problem was that Mark, when he published his video, he put them out of order. So that's
He put
probably
them
why
out
I
of
confused
order.
it.
I lost track. We did way more than we ever thought we would do.
Okay, so I'm just going to share my screen.
Oh,
Not
yeah,
that one. That's not the one I want. Oh, yeah, it is. Okay. So basically, I'm just going to share. So this is us sort of building that first version. We used polycarbonate storm sheeting, and we ended up using these little hinged plastic panels that I found on a plastic supplier, because we were trying to make sure that like we could still have it sealed in the middle and go all the way around, and also be easy to assemble, because like we didn't want to have to be like doing all sorts of fiddly bits with this, but ended up being that way. So you can see the first one worked pretty well. Let me play that kind of montage of us building it again real quick. So you can see that's the polycarbonate storm sheeting, and there's a bunch of those plastic hinges there. So the neck was very narrow on this first one, and you can see it failed. It exploded on the side. So one of the things that we discovered was this generated a lot more pressure inside than we expected. And I mean, when you think about it, a glass flask is super strong, but like it's just foam, right? It's like both Bob and I were like, oh yeah, huh? Because when you think about the foam, you don't actually really think about how much pressure it's generating. And there's no way to really measure it, the pressure inside of a glass flask. So we couldn't like calculate how much it was going to scale up. So basically it burst at one of the seams. And I had the idea of using flex tape before we even built this one, just because I'm kind of a tape nerd. We'd done a lot of sort of analysis. Let me say, I have done a lot of experimentation with different types of tape. And I found that flex tape had the highest temperature tolerance because this chemical reaction gets pretty warm. What was the temp it gets to, Bob?
Got to 180. 180.
Yeah, it goes pretty high.
Really
but the way we built this first one is we kind of laid it out flat and then we folded it up. And because we built it that way, we couldn't seal the inside of one of the seams with tape. And that was what resulted in this failure. So it went still pretty high, went something like 30 feet high. This is our second test. So pretty much the same design. And it also failed. You can see right there in the middle, we did some additional strengthening. And we tried to sort of, that's sail repair tape. So it has a very, very high tensile strength. And it's just ripped right through it. So there are a couple angles here of these. And this was built similarly, but we thought we had done enough. However, we didn't quite do enough. So you can see, I'm going to pause it right about there. You can see that it starts to expand. It gets, the pressure on the inside is very high. And it explosively decompressed, basically. And you'll notice that this is a little bit of a trend, but so we took that information and said, okay, we've got to figure out how to make these sides stronger. So Bob and I spoke to Mark a number of times. We kind of evaluated a bunch of different ways of doing it, and we ended up building an entirely new one. Right, Bob? We scrapped, oh, no, sorry. This one was the new one. this one we scrapped. The first one we scrapped.
Yeah, we trashed.
Yeah.
What was kind of fun about this was it was like totally an exercise in material science. This is kind of where like Jacob, he just knew materials that I didn't know, but it was we got unexpected stuff. We assumed we could scale it up. Turns out the chemistry scales, but the physics, in other words, almost like a ratio as far as how much foam goes. You double the chemicals, you get double the foam. But the pressure was
almost exactly like a linear scaling.
Yeah.
And it was actually at this point that when speaking to Mark, we decided that we needed to figure out exactly how the chemical was scaling, because he wanted us to just see if it went high initially. And the answer was, yeah, it can go high. So then we had to like actually get some math in there.
It was kind of just a shout out to Mark, because it's easy to think, oh, Mark doesn't do his own things. He just like takes credit for other people's work. He was like after every experiment.
Oh yeah, he was on top of everything.
He was making. He's like, try this, and Jake would be like, oh, that means we got to build another one.
Yeah.
But no, but we like the challenge. So, like, it's definitely his handprints are all over that. It's not just us.
Yeah. So one of the things that was super beneficial was he actually had a couple people helping him out in California doing the same experiment in just the small flask over and over again with different ratios of chemicals, different concentrations, until we could we optimized it. And Bob did a bunch of them here. They did a bunch of them there, because we found differences in food coloring and differences in different things would change the reaction. So there were a lot of moving parts to kind of dialing in the final experiment. But it was at this point when this second one exploded as well that we realized we really needed to figure out that formula for what we wanted. Because one of the kind of parameters for the final version of this was that it looked like the tabletop version, but just way bigger. And so, Bob, you want to explain a little bit about like the confetti versus laminar?
Yeah, so we wanted the tabletop version goes up, stays in a column, comes down, doesn't go confetti. We were going for a world record for height, and the actual world record for height, they do this experiment in a 5-gallon water jug, and it just goes confetti. It goes like 30 feet high.
So when he says confetti, it's because they use the chemical reaction that they're using is a different formulation. So it's much higher pressure. It's a much faster reaction. So it more sprays out of the top than it does kind of come out in a column. It just like goes instead of like a nice laminar column.
Yeah, we wanted to go. That was like Mark's big thing. He wanted it to look laminar.
Right, and it looks cooler in general. So.
Yeah, and we just felt like we were cheating if it went confetti. We were just cheating. It's too easy. And so we kind of got it. We did both versions. We blew it out confetti once. We went laminar, but we didn't get height. And then it was all about, in the video, Mark talks about it perfectly. He does a great example. We'll show you a little insider thing that no one saw before. Is we one of the things we tried was these little guys. And I don't know, can they see this? You're still your screen sharing?
Yep. Oh, wait. Yeah, it's in your video. I think they should be able to see it.
So one idea that we talked to a fluid dynamics person here at the Artisan Asylum, they said, well, if you have like almost a straw setup inside, you're more likely to get laminar. So we printed a number of versions of these. I got more of them. So we used different size flasks that had different size necks, and we created these. And
stop Jacob sharing just so we can see that, Bob, just in case in the recorded version. All right, keep going.
Oh yeah, makes sense. Yep.
So we tried these, and it turns out they still went confetti. If we really stuck with it, if we saw a big difference, we'd tweak these things. But again, this was experiment. You don't see it in the he talks about it, but you just don't know. It's days and days of experiments and experiments.
Yeah. So like I said, it was at this point where like we were trying to we were dialing in the chemistry, and we were also experimenting with other ways to make this look the way we wanted it to. And one of the things that I kind of tried to advocate, which didn't happen, which it ended up working out anyways, which was to change one parameter at a time. And that was something that we were all kind of not doing a great job of doing. This second test, we used a different formula from the first test. And the test after this, we also used a different formula and a different flask shape. So it was kind of like, there was a point where we were like, oh, wait, we need to make this a more controlled experiment. So I'll reshare that, the next experiment, and show you why we felt that way. So what we did is we were like, oh, it's spraying out a little bit too much. We want it to be a little bit more laminar. So we want to, we'll widen the neck, right? And we widened it more than we thought was necessary. And so you can see it was very laminar, but it didn't go nearly as high. And so this is kind of the point where we all said, okay, we've got to dial this in a way that isn't gonna kind of add more variables to the environment. So they dialed in the formula we wanted to use in the tabletop version. And that was a combination of Bob and the guys out in California doing probably a total of 50 or 60 tests, I imagine. And we dialed in that formula. So we tested it again in this one. I actually don't know if I have footage in that, and it didn't really help. So we said, okay, we need to narrow the neck. And that was the parameter that we wanted to change, because we said, we have this, we have the thing we want. We tried the honeycomb in the little version, it didn't help. We tried making the neck longer, like Bob said. There were so many different variables that we tried, but we tried one at a time in the small version. So the next version, this version looked really, really cool, especially in slow-mo. It was super laminar. There was almost no like extra stuff spraying around, but that's because the neck was so wide that the pressure wasn't high enough to actually push it out.
Also worth noting, each time we did this experiment, it's hundreds of dollars.
Oh, hundreds and hundreds, yeah. So that's why we decided to I mean, that's why Mark decided, but that's why we all decided, okay, we should dial in the chemistry and the shape in the small version. So
and it's clean up and building, and we have to find a day that's not windy. Like
right.
There's all this stuff going on.
Right. We have to find a day nobody's in the loading dock. It was So one of the things you can actually kind of see in this one here is we also added some additional strengthening on all of the seams. And basically we changed the entire way that we built this so that we could seal every single internal seam, which was being problematic. And then there were metal bands around this. And it still leaked out the sides, but not explosive decompression. So we actually had some pressure measurements and temperature measurements on the inside of this, and it maxed out the pressure sensor. I don't remember what it maxed out at. Do you, Bob?
It was weird. It was like 1.8, but I don't remember which.
Yeah. It basically was an invalid measurement. So this was my sort of optimization of this neck. And as you can see, it worked like pretty close to perfectly. The beginning of it is a little bit feathery, and it kind of like separates up near the top, but this was our proof of concept. When this happened, we were like, that's it. And we knew that it was a little bit too narrow. The neck was a tiny bit too narrow. So like basically I had a huge Excel sheet of all these different tests and all the parameters that we were changing, from neck size to neck length to all of that. And that was really important. I can't tell you how many times Bob was like, wait, which formula are we using again? And I was like, Bob, check the spreadsheet, Bob.
And
so many times.
so many. It's like the spreadsheet. Well, we can't show it. If you go on my website, I do have a snapshot of the of it, but it was so much work. Like for now, we're kind of keeping it to ourselves because
For
it's
reason.
too easy to duplicate. Yeah.
Yeah.
Also, Nick in the chat asked how long does it take to clean up. So there's two things that are kind of interesting. Number one, the chemical is super dangerous. Like if you got it on your hydrogen peroxide that we used, if you got it on your skin, you're going to get a chemical burn, and it'll be painful. If you get it in your eyes, you can go blind. When the reaction is complete, you literally end up with soapy water and some iodine. So it was able to be like go into like the town sewage because it's not much different than like a bubble bath. So cleanup was just a matter of hosing it down. And depending on how well the reaction worked, it was probably 15 to 20 minutes of just hosing it down and diluting it. So yeah, we get that question a lot of how do you do
It did stain a little bit, but the sun bleaches it away pretty quickly.
Yeah. The iodine, it's actually not the iodine is worse than the food coloring.
Right, yeah. Yeah.
The chemical reaction creates soapy water and iodine. And if you ever did iodine experiments in high school, they do stain your skin.
So yeah, so after we kind of dialed that in, we started trying to like, we took my model. Actually, let me share that. Let's see. Sorry, I have too many monitors and too many windows open. So we did a couple different things. So the first one we did is we show all windows. Come on, where is it? There it is.
What do you think our total bill in fastening materials, screws and nails and things was?
In just different types of fasteners we bought, it was probably like $150.
We went through a lot of interesting fasteners.
We did, yeah. So what I ended up doing is once we took that 4-foot one, I scaled it up, and then I started kind of mocking up how I wanted to actually, oh, come on, I'm on a trackpad here, sorry, how we wanted to actually build it. So in this case, we used some 2x4s on each seam and 4x4s on the bottom, and then bolted it down to double thick sheet of plywood base. And we kind of went from there. I can share the video of us building it while I talk. Is that still showing Fusion, or is that showing my? That is not showing the right one.
Fusion.
Yep. Sorry. So as we built it, we kind of came up with additional ways to do some strengthening, and we had to figure out ways to kind of jig the sides, because it actually got pretty necessary for us to have very, very perfectly sized sides, because when they all come together in the top, if they aren't all exactly the same size, you're going to have a big gap in your seam. So this was basically how we built the 10-footer, and there's a bunch of missing footage in here because I had a hard drive failure, but you can see all of the kind of flex seal on the inside here on each seam. We just got some flex seal for that. And we had to come up with a sort of door system for this. Bob, do you want to talk about how we worked out the dumping mechanism?
Yeah, so one of the challenges, it's like, okay, now we are going to mix two chemicals. We can't dump it into the top. That's not an option. So
this one was a little over 12 feet tall, right, Bob? Oh, no.
Yeah, I can show you kind of to scale. This will kind of give you a little scale there. So we had to do some kind of a dumping mechanism, and we ended up going and getting, I believe, a 13-gallon tote from Home Depot, and hooked that up to a hinge and a latch. The latch is a pull latch. So that had a cable, an airline cable that went through the side of the flask. And then once that's pulled, the latch is released. The chemical tips over, and that dumps it. We did make a critical error in that it turned out that and it's terrifying because you have to fill the catalyst and then you have to fill the hydrogen peroxide. If something went wrong and that tipped over, then we have humans in the middle of a 100-degree violent chemical reaction. And when we ended up doing the measurements, it just came to the top of that container. So if any spilled out, we're in trouble. To the point where Jacob had to throw some flex tape around it just in case.
To make it taller. Yep. So yeah, that was kind of like an unforeseen calculation. And I think that actually had to do with technically the volume that we were mixing should have fit in the dump bucket that we picked, but we didn't calculate for the additional like dissolved catalyst volume, which would increase that just enough that it would almost dump out. So one of those sort of
my job was to watch that container, and it wasn't a very sturdy latch. It was
no, it was a little bit scary.
My job during that filling was to watch that bucket, and if anything happened, I yelled run, and whatever anyone did, they just bolted it in case something was going wrong. And Jason was like our hero in filling that. For those of you that know Jason, he's the unsung hero in that day.
Yeah, there's a couple good clips of Jason in my video. So the plan initially was to use some ratchet straps around the 10-foot version to make sure that it wouldn't bow outwards because we knew that there's going to be a lot of pressure, right? So we're loading it up onto the pickup truck, and in a way, Jason's also the villain of this story because we had it all strapped down to the tow truck, which is a whole different story. We had a truck rented. I went to the U-Haul. They told us they gave it away to someone else and wouldn't refund us. And yeah, it was bad. So then we had to end up calling a tow truck, which was Bob's original idea. And got it all strapped down. And I was like, Jason, make sure you grab those ratchet straps that are on the floor inside the loading dock. And he's like, yeah, I got it. So we get there, we're filling it all up, and like everything's ready to go. It's all together. And I'm like, okay, where are the ratchet straps? And he's like, what ratchet straps? So that was a little bit of a problem because there was a small leak in the bottom of this giant flask. Small enough that it was slow and we weren't super worried about it, but we were worried enough about it that we couldn't postpone the test to go get those ratchet straps. So we put one on probably like a couple feet below the top neck where we thought the highest amount of pressure would be. And then we had to wait a couple minutes because it was pretty windy. I'll share my screen again. So I don't know if you've seen this video or not, but this is my favorite angle from this. So we pull it, and I'm running away after pulling that cable, and I just hear this loud bang and this crack behind me, and I turn around and the foam is maybe 3 feet from my face. You can see me kind of scoot out of the way there. So those walls are 27 feet high, and you can kind of get a sense of how tall this thing is. It was pretty darn heavy. So you can actually see in a couple different shots here just how bad that damage was. It wasn't necessarily a failure of the design. It was just a failure of the materials we used. Those are 2x4s that snapped in half, just like twigs. There were a couple different.
All of our experiments, with the exception of one, in all of our larger experiments, even the 5-footer, we broke the world record.
Yeah, every single one. So this went about 65 feet in the air, which is, 60 is what we said for this one, which was like just blew away the world record. But we didn't document it in such a way that we could then submit that to Guinness and actually get the world record. but we knew we were going to go higher. So you can see if you watch really closely just how, no, sorry, I think it's the next one. Yeah, you can see if you look really closely, the seams actually split apart. And you can see the flex tape actually hold them together. So that choice of that tape was like the perfect choice. But I still think that the reason that this one broke was, one, because we were missing the ratchet straps, because if that had had a ring around it to keep it from flexing, those 2x4s would not have snapped. But something else may have failed. So the amount of pressure in there is still huge.
Actually, maybe the bottom would have failed, and then
yeah, we think the bottom would have failed. Well, so I actually am not sure about that, because we had 4x4s along the bottom, and this is where the discrepancy occurred. We'll talk about the big one in a minute. Why that happened the way it did in a minute. So I almost didn't go out to California. We were working with a guy out in California named, Mark, obviously, and then why am I totally blanking on his name?
John.
Oh yeah, and John. Marku, yeah, who has worked as a prop builder and fabricator for like Adam Savage's TV shows and things. Makes all sorts of insane stuff as a job, which is something I'm a little envious about. But we got there, we started building it, and pretty immediately upon starting to build it out of wood, we were all like, oh yeah, we should have made this out of metal, but we've already started, so we're going to keep going. I got there and the base was already built. It was pretty much done when I got there, so I was just kind of gung-ho to get going. And you can see that base doesn't look super thick. And so one of the things we cranked away at it. It's probably like 3 12-hour days, Bob?
Oh yeah, for sure.
Easily. So it looked awesome. It was so hot out, and it was also smoky. So this is probably the clearest it was the entire time we were there, because it was right around the time of the fires. And we finished it just in time. Like we finished it maybe an hour before it was ready to be tested. The morning of, so this is the night before, we were in there taping everything up and getting it working, right? So the morning of, stop sharing now. I
gotta do questions, man, just so you know. Yeah.
I know. I assumed Anne would stop us if we needed to stop talking.
I was sending you private chats, guys.
Oh, you are, hey? Oh, hey, look at that. Cool. Awesome. So, watch the main video. I'll talk about why I failed real quickly. So the morning of, Bob was like, hey, Jacob, make sure that everything's screwed down into the base. And he was like, I'm a little worried about it. And as I was screwing it down, I was like, oh man, the 10-footer was only 2 pieces of plywood thick. And it also had horizontal structure. This one was only 3 pieces of plywood thick and didn't have horizontal structure. So what ended up happening with the big one is the whole thing is shaped just like a rocket engine. So it actually functioned just like a rocket engine. The foam basically pushed it down and the bottom exploded out and it lifted off the ground. It went probably, we decided like almost 6 feet off the ground?
5 feet, yeah.
So it was really, really incredible. But like, it was interesting because there were probably 4 or 5 engineers working on this, and a scientist, and a bunch of fabricators, and we all just sort of like missed that one little detail.
Well, that's actually a really fantastic segue, Jacob, because I wanted to ask, you've talked a lot about your process, sort of the iterative design, using sort of the scientific method, and I heard a lot about Excel spreadsheets. So in this planning process, can you talk a little bit about how you plan for failure? One thing I try and advocate for in anything we do with sort of STEAM STEM education is that we talk about failure and how it's a necessary part of the process. So how do you plan for failure?
I don't know, we plan for failure. we accept failure, and then we
Learn from it. Yeah.
learn from it.
Yeah.
Right.
So basically, in this instance, I treated every failure as a data point, because we knew we had an end goal of this thing has to work, and we knew we had an end goal of this thing has to at least do something close to this thing by this point in time. So the time crunch was definitely hard, because we could have, if we had iterated on this a little bit more, we would have spent a lot more money and not had much more yield, if that makes sense. So it was definitely be prepared for it to fail. Don't necessarily plan for it to fail, but be prepared to learn from it if it does fail and use that information to improve your process. And it's sort of like, it's not my motto, it's kind of a maker motto that's happened over the last few years, but it's like fail, make, fail, make, fail, make. Learn every time.
We did it enough that a lot of it was looking at the data, and then sometimes we just stand around and go, you know what, my gut says this is the diameter.
100%. Right. Yeah. So the final diameter we picked was 100% a gut feeling from my end, and Mark specifically wanted it. Looking at the data, wanted it bigger. But I was like, no. Like, I really think it needs to be 3 inches narrower in order for us to get what we want. And it ended up working beautifully. And so sometimes there is, based on the data, you might have a gut thing, because we didn't have all of the science and math done for all of the like fiddly little chemistry stuff, but we had done it enough times that we kind of had a good idea as to what it would do.
And then at one point they're like, I wonder if it's like literally 110 degrees in Gridley, California. Is that going to affect our chemicals?
And we were like, oh.
2 days before I left to go to California, I did a test, and it turns out it's a huge difference. So we literally had to get 2 air conditioners in a pool shed and keep our chemicals in there so that they didn't increase the reaction in ways we didn't want.
Yep.
It's nuts. Crazy.
I wanted to ask you a question, which is, so you started out saying that, you know, you're a classroom teacher, you teach sciences, and what wasn't sort of talked about in this whole thing is, well, 2 things. One, you guys were doing this all in the time of COVID. You did mention that Mark had gotten COVID, but you were planning and coordinating this whole thing during COVID. So I guess sort of my question is I sit in a lot of meetings with local teachers, and we've sort of shifted everything to virtual. And in fact, you know, Artisans, while we have some hands-on classes, you know, we're also building out virtual courses. You have a unique experience where you've done some classroom teaching, and then you also get these experiences where you get to do things on television or social media. You have your own social media channel. I'd like to just hear from you for a few minutes about, you know, where do you think these virtual formats have a little bit of an edge over sort of traditional classroom teaching? What kinds of things can you do, you know, virtually that you can't do in a classroom?
Well, I'll tell you, I just got my hands on a Oculus virtual reality thing. If you ever get your chance to try this out, Adam Savage from MythBusters did some shop builds from his shop in virtual reality. And when you put the goggles on, he is standing in front of you, your full size, his work table's right in front of him. And he's like, I'm going to show you how I make a thing. And that would be impossible even in a video format. Obviously, ideal would be, hey, you go to his shop. But then if you get a chance, you know, you watch a video. So virtual is tough. It's just because it's fatiguing. In some ways it's better. I can have a second camera and I can do close-ups. I can play back videos. I can, doesn't matter where a kid sits, they're all seeing the same thing. They're all at home. So there are some advantages, but the fatigue is tough. All right. And that's, if they do it for a whole day, it's rough. But we've seen this thing with Adam. We put it on the Oculus. and showed it to a bunch of teachers, and they're like, this is could be the next thing. This could be a whole classroom of kids in Oculus and VR glasses.
I think for me, one of the things that in terms of like, if you just say virtual, it's kind of a little bit too broad for me. But if you kind of dial it into YouTube or people who create content, whether it's engineering, science, or just doing ridiculous things with money because they can, which various opinions on that, obviously. But one of the things that I think I've seen it do with kids and up to me even is kind of give me a baseline for like, oh, they can do that. That means I can do that. Or that means I can do it better. Or kind of, it stimulates the imagination in a way that it wouldn't necessarily in a classroom. Obviously, getting a kit to build a catapult and building a catapult on your desk is going to be more enlightening in many different ways. But seeing somebody build a 30-foot tall catapult and throw pianos out of it because they can also does something to your imagination. But it's kind of joining that feeling, because some people see that they're like, oh, I could never do that. But it's joining that feeling with, no, you can do that.
Mhm.
That is really important, I think, in this kind of virtual day and age.
Yeah, when we originally sort of talked about this, I'm sort of in that space too of like, oh, you're down in the trenches. There's, it's a very tough transition. But one of the fascinating things and why I brought you guys on was to kind of have a moment to just be able to step back and to look at something like this of like, oh my gosh, you can create a 20-foot tall flask and blow stuff up in it and get a world record out of it. So I have one last question really quickly, and then we'll turn the time over. We've mentioned Adam Savage a number of times in this call, and it's so funny because Adam Savage on his series Ask Adam just put out a video and happens to name drop you a little bit, Bob, Science Bob, and he mentions you, and then directly after that, he's talking about Artisan's Asylum because he's talking about maker spaces that he's visited, and he immediately starts to begin to talk about describing Artisans, and the thing that he kind of the words he used were sort of messy, in process, lots of stuff. So do you think there's any relationship between what Adam Savage saw and your studio? But really what I'm getting at is, even though there is sort of that messiness to it, I think what is unique about Artisans and what you guys do in your space is sort of celebrate that process and also celebrate some of the things that may not have worked. So is there anything hanging up in either of your studios? Jacob, I know you're not there.
Oh, I have my own little workshop going on here, don't worry.
So anything that you've put up where you're celebrating some sort of failure, or you're putting up a challenge to yourself of, I never finished that, or it didn't work the way I want it, and it's an inspiration to yourself.
All right, stand by. Hold on.
Okay, well, he's finding his thing. The answer is yes. So 2 years ago, I started a duct tape project, 2 or 3 years ago. And it's a Star Wars vehicle. It's Slave One. It's Boba Fett's ship. And it started out and it looked really awesome. And then I took it apart because I didn't like how it was working. And then I worked on it again for a bit. And a year ago, I posted my first YouTube video on it, or my second YouTube video on it. So that was a year ago. This is its current state. 2 nights ago, I chopped it in half because I didn't like how it was working. And I had challenged myself to make this in such a way that I don't need to fix it in the future, because many of my duct tape projects require some repair over time. And so there's this large cantilevered portion of this that I had to figure out a way to get it to stay. And so like, it's not so much necessarily I mean, the challenge to myself is to finish this because I've had it on my to-do list for so long. But also, it's like all of these duct tape projects that I've done have always been challenges to myself. Like, this looks like a difficult problem to solve, making it entirely out of duct tape. I want to solve that problem. So for me, that's my current unfinished / hasn't worked 3 times project, because it goes up and down. When it doesn't work, or like I work on it for 3 weeks, right? I get distracted by the flask for 3 months, and then I come back to it and the whole thing has collapsed. That's a pretty frustrating process. But my challenge to myself is to push through those failures and make it so it doesn't collapse when I leave it for 3 months.
I decided one day to build a Venturi effect ping pong ball rapid fire cannon, because that's how I roll people. And so I figured, oh, this is great. I'll get a big bucket. I'll funnel them down into a hose, and then they'll go into the blower and it'll be great. Well, it turns out ping pong balls do not funnel. They get stuck. They're like a non-Newtonian fluid. So I said, all right, I got to build a propeller system to launch it. And I started off with a bowl, and then I switched over to this, and I put a motor on it. Then that didn't work. And then I built a little spinner device, and that one didn't work. And then I built another spinner device, and that one was at the wrong height. And then I made them bigger, and I built another spinner device, and that one didn't work. And ultimately, I built it on a little disc, and that remains inside of it. So that was like 5 failures in a row that no one will ever see until now.
All right. Well, thank you so much, you guys. But Bob, Jacob, thank you so much for pioneering this new virtual series with us. I'm so delighted that you agreed to speak a little bit about this entire video. It was a lot of fun to watch. It had so many connections to what I've been thinking about. How do we just get people excited and engaged in sort of the scientific process overall? So thank you so much for your efforts, and thank you to everyone who joined us today. We'll sort of wrap up here, and hopefully you will join us for the next one. Not January, but February. I'm hoping to have a really super cool artist, woodworking artist on joining us and talking about his process. So thanks everyone. Have a great night.
Goodbye. Thanks for joining us, guys.